Welcome back. Now we are going to add actions to a smart contract. Our goal is to send ADA to this contract and get the address of the contract. Saying hello world is good, but it's not enough to build our crowdfunding contract. So let's start adding the actions that will help us achieve our goal. We need to add an action that allows users to send money to the contract. But for users to be able to do that, we know what's the contract address we are sending money to. So let's define a helper expression that just computes the smart contract address and returns that. That expression will look something like this. Plutus playground, okay. Let me do something. Here we have the contract address expression. This expression has type address, and it's defined as the result of applying our myValidator script to the validator script address that takes the value of type validator script, like our myValidator script, and returns of type of address. So, very simple. Now, we can implement the wallet action responsible for sending money to the contract. Something like this. We have the endpoint is called contribute, and is of type of a context monad wallet that receives an ADA and returns a monad. Now we know that the wallet action can be and will be registered as a contract endpoint for users to interact with. We know this due to the type of the expression monad wallet. The contribute action is an expression that takes some amount of value type ADA and returns the wallet action defined below. Now, we defined contribute that receives value and then the do. The do after the equal sign in the definition of the contribute expression, we can use this notation in Haskell to construct a sequence of actions as if it were only one big action. In this case, we are going to use the onPub key and pay to script log message. Now, the first thing we do is extract the user's public key using the onPub key action. We will use this to identify who's making the contribution. As in the extended UTXO model using the Cardano, we can tie information to the coins we send. This will later be useful to refund users' contribution if the crowdfunding campaign doesn't reach the target amount. In order to pay the amount, we need to provide 4 things that are calculated here. We can do the data script that allows us to create a valid data script that can be stored on the blockchain alongside a transaction. It takes a listed representation of the value we want to store in it, in this case, on primary key. And values of this type can be lifted or transformed to an on-chain representation. This is what the ledger lifted function does. It prepares the value to be used in blockchain by lifting it so we can use it as a data script. Then we will also need to calculate the range. The range expression is a time-based slot we use to specify when each transaction is valid. For example, we could flag this transaction as invalid if the current loss is before some time we specify. In this case, we want to accept contributions at any time. We will change this later. So we use the default slot range that gives us the range that basically says always is valid. And then we will need to provide the amount. we just transform the ADA amount to a value. Value is ultimately what is stored in the blockchain. And finally, we will use the pay to script function to create and broadcast the transaction. Let's recap. The contribute function is going to take some ADA and create a wallet action. Then the primary key will get the current user's public key as its own primary key. Then create a data script with own primary key. Then range is the transaction when the transaction is valid, and then we have the value amount to send. And finally, create and send transactions to the contract address that is defined here at the top. Lastly, we should, send a message so that we know that the contribution has been submitted. Now, as you know, the last step is to register the contract endpoints as an action available to the customer. And we do that as we did that before with the MK functions. Function here. All right. Now let's compile. Let's compile our code. No. I made a nesting error. There you go. Okay. Now you see that now we have the contribute action. And let's do some contribution, basically 20 ADA, and then let's do both another contribution, and he will do 5 ADA. And await action at the end. And if we evaluate this, you should see that Alice wallet is only 3 ADA because she contributed 20, and Bob's ADA is 5. It's 45 because he contributed 5 ADA to the contract. And here you can see in the log messages the participation of the log that we did. Okay, so although our contract is working, there is something we can do to improve the logic. For example, right now, we are not performing any validation in the contribution. So it's possible for a user to add 0 ADA contribution. Let's correct that by checking at the beginning of the contribution code. So what we're going to do is right here, if value minor or equal to 0, throw the error, must contribute a positive value, else we can continue the action. Now, another thing we can do to improve our code definition is to change the type of the data script validator script. Right now, the data script, the validator, is like this. And that data script returns a type unit. But this is no longer true. Our data script is a proof key because we are reusing a value for this type to create the data script we are sending along with the contribution and contribute action. So let's reflect that change like this. So our data script now return a post key. Like so. And the rest of the code looks the same. Alright, it did compile, and as we know, in Haskell, if it compiles, it works. Well, that's a joke, but it's close to reality in our case. And now, in this lesson, we created a contract that is able to receive contributions from multiple users. We did using the pay to script function. That is right in the pay to script function right here. In the next lesson, we will add a little bit more of code that will allow your users to receive a refund.
In the previous lesson, we created a contract that is able to receive contributions from multiple users. We did this by using the pay to script function. In this lesson, we will add a little bit more code that will allow users to receive a refund from their contributions. Our goal is to add the ability to refund people that contributed and create event triggers and handlers. Our code currently looks like this. We have the contribute action, the contract address, hello action, and we will eliminate the hello action. We don't no longer need it. The MK functions around here. There you go. Now, in this lesson, our focus will be to work with the contribute action that currently is this code right here. Now, let's add the ability to refund. At this moment, we do not provide a mechanism to pull out the money users have sent to the contract. What we will do next is to automatically refund users' contribution after some slot has passed in the blockchain. In order to set up that automatically, we will make use of the event triggers and event handlers. Let's introduce each of these concepts. By using both an event trigger and an event handler, we can subscribe the user's wallet to react to certain events involving the smart contract of the blockchain state. He will use them to return a user contribution after some slot has been reached. Event triggers. An event trigger is a tool provided to us to define when certain actions must take place. For example, we would like the user's wallet to take some action when the wallet in the contract exceeds some specified amount, or take an action when some deadline has been reached. We will go with the latter. Let's set up an event trigger that will fire when the current slot is greater than 15. So, here we have refund trigger that is of type event trigger, and the definition of the function is like this. This is a simple trigger, an expression of type event trigger by using a slot range t. Function, we create a value of this type. We only have to provide it a slot range value of which we wish to dispatch the event trigger. In our case, we want to dispatch the trigger when the current slot is greater than or equal to 15. So we use the interval from function that allows to construct such a slot range. It is important to note that the trigger will dispatch for each slot that satisfies this condition. The action will be run once for each block where the condition holds. For example, register slots T range interval 3 to 6 causes the trigger to be fired at blocks 3, 4, and 5. Now that we have an event trigger, we need an event handler. Event handlers allow us to set up what actions are due to be performed when the condition specified by the trigger is met. In this case, we want to refine users that send money to the contract. That's why our event handler should do. So the code here is a little bit like this. We have here the refund handler. that is type, it's a monad wallet, takes a transaction ID and returns an event handler. Now, the definition is, let's do some logging here. Let's create the redeemer script that just returns everything and the range. We have here the redeemer script. And now the range where this is valid, and also the collect from script. Let's see what is going on here. Our refund handler expression is a function that expects a value of type transaction ID right here. And this is the transaction ID of the contribution the user made to the contract to return an event handler that executes in the context of a wallet action. In the definition, we use the event handler data constructor to build a valid event handler. We pass to it a lambda expression, and its only argument is the event trigger. It's the event trigger that causes this handler to dispatch. We don't care about it, and that's why we ignore it with the underscore. This lambda expression should return the action that the handler is supposed to run. In this case, we log a message out and define some local expressions, a redeemer script, and a range. We need both of these things to create a transaction that will allow us to retrieve funds from the contract. But using the collect from script TXN function, we create and broadcast a transaction that attempts to spend the UTXOs currently associated with the contract to an address owned by the user, sending the transaction the user's wallets in this case. In the same way we provide the range when using the pay to script function, we do the same here. The transaction will only be valid within the specified slot range, this slot range here. In this case, our range goes from slot 15 onwards. Unlike last time, we don't need to provide the smart contract address, but the smart contract itself. That is the validator expression right here. The other argument we provide to this function is the redeemer script. This usually contains a proof that we are allowed to spend money from the contract. Since we are not performing any validation in the validator script, we have a dummy validator for now, we don't need to provide any proof. That's why our redeemer script, right here, contains just a unit. Note that although it's a unit, it still needs to be lifted. The last argument we need to provide is the transaction ID. This makes the action only try to spend the outputs associated with the given transaction ID. For example, Alice makes a contribution by sending transaction A. Bob sends another contribution in a transaction B. Now both Alice and Bob will receive refund, but to know which contribution is which, we ask users to provide a transaction ID that originated from their contribution. This way we know which coins are Bob's and which are Alice. Next, we need to register both the trigger and the event handler. At this point, we have defined both an event trigger and event handler, but they aren't registered yet. We will slightly modify the contribute action to register the handler to the trigger. So our modification in the contribute is here in the pay to script. We will change it for TX. It's a pay to script. We will delete the underscore here and range contract address, amount data script. Long message submitted contribution, okay. And now we will register the triggers here. Register refund trigger with a refund handler that takes ledger hash transaction. Take a look at the first change. We no longer use the pay to script underscore function, but the pay to script function without the underscore. This means that the resulting transaction, the one that was just created and broadcasted, will be given to use as a result. We capture this value in TX. Next, we add a call to the register action. This function takes two parameters, the event trigger and the event handler, to be registered. These are expressions we just created above. There is one more thing to note here. The TX value has the type capital TX, and we need a value of type TXID. It so happens that the ID of a transaction is just its hash, so we use the hash TX function from the ledger module on the TX value to produce the transaction ID we created for the refund handler we created. Now, let's simulate the contract. Let's compile the code. What is the error here? This one should be here. Compile. Here we need to register the MK functions that it's adding for our case. So we just need to create MK functions to register. Okay, functions. Contribute right there. We compile this. Here. Mismatch brackets. Font handler. It continues to be here. This is like a virus. Just delete it. There. Compile. Okay. Here, this TX is a TXID. Compile. What is this? Autocomplete. There you go. Okay. Now, let's say Alice got 100 ADA, Bob got 50, and Carol got 30. Each of these wallets will act as a contributor. So for each one of them, add the contribute action with multiple amounts. Well, let's say Alice contributes 11 ADA, Bob contributes 22, and Carol contributes 27 ADA. Now, we add a weight action of 10, and if we evaluate this simulation, we see here that they got all their ADAs. Why? In the log we can see it. In the first slot, wallet 1 submitted a contribution. It's a weight action that it's longer, and evaluate this one. And let's see, ignore this part. Here, the wallets are trying to claim their fund. And from the slot 15 onwards, the event trigger continues to happen. And this way you can see that the trigger was executed. So, in conclusion, in this lesson we learned about event triggers and event handlers. We use them to implement an automatic refund action for the user's contributions to the contract. In the next lecture, we will implement a new wallet action used to collect the whole raised amount in the contract, because currently the trigger only is useful to send money to the smart contract, and then starting on the slot 15, getting the trigger to return the raised amount.